Okay, I'm going to go over this one. This is a nice, easy start for parametric for a free response question. It's probably a little easier than what we're going to actually see, but it's a good one to go over. So starting with, see if I can do it like this. You can see the problem as well. Got the board back, so hopefully this will be easier for you to see. Okay, so during the time period from t equals 0 to t equals 6, a particle moves along the path given by x is this and y is this. Find the position of the particle. So first of all, just understand that when you see x of t and y of t, these are position functions. Okay, they're telling us those are the position, this is the position of x and the position of y based on whatever time they're giving us. This is also a calculator problem. Where is my calculator? Here it is. So that's good, we'll be able to use the calculator. Okay, so to get the, sorry, I'm just gonna get my answers out so I don't have to take the time on the calculator and waste your time. Okay, so find the position of the particle. All we're doing then is plugging 2.5 in for the t in both the x and the y. So remember, when I'm graphing parametric stuff, I'm still graphing on the xy plane. It's different than polar. If polar is something that you even remember at this point, that's okay if you don't. So to find the x coordinate, I'm plugging 2.5 in for t, and the same thing for the y. Oops. I'm plugging 2.5 in for t. And I'm using the calculator and I'm getting the numbers for those. So the number for the x turns out to be 0. The number for the y turns out to be 5. Find the position of the particle. That's it, 0, 5. If I were to graph it, I could graph it. It's at the 0.05. Okay, that's all that they're asking you to do for that. Part B, now we're going to graph. So in the axis provided below, sketch the graph of the path of the particle from t equals 0 to t equals 6. Indicate the direction of the particle along its path. I think I mentioned something like that in the notes of, they sometimes want us to indicate direction. So in other words, I'm going to make a little t-chart here. I'm going to have t on it now with x and y. And since t is going to start from 0 and end at 6, I'm going to start with 0. And I'm going to see what happens as I start to graph, or start to plot the points. So let's see, if I plug in 0, I'm going to get, I have my functions up there. So if I plug in 0 for t in the x equation, I'm going to get 3. If I plug in 0 in the y, I'm going to get 0. And I could move on by whole numbers. So let's see what happens. I first want to try moving on by whole numbers and see. So let's say t is 1. What happens? So when t is 1, I'm going to get -3 for the x and 0 for the y. So let's graph that and just see what we have. So I have the point 3, 0, and that's where I'm going to start. Put a little note to myself that, oops, that's not working. That's where I'm going to start. But then I have the point -3, 0. Well, how does that doesn't help me a whole lot. It doesn't help me see what the curve is actually going to look like. So I might need some fractions. I might need to get some numbers in between 0 and 1. Do you love the dog? I'm going to kill him. So I'm going to try plugging in a half and see what happens. So plug a half into my function for x, and I get 0 for x, and plug a half into the function for y, and I get 5. Well, that's a little better. Now I have a point at 0, 5. There are a couple assumptions you can make with this. You can assume that things are going to be pretty smooth. So how am I going to get from this point to this point? I'm probably not doing something funky like that. That would make no sense. I'm also probably not attaching the 2 points with a line, especially because my functions are sine and cosine. It's going to be something that's like a circle, curved, whatever. So this does look like this. And what does it do after that? Well, let's see what happens when I plug in 2. No, actually, I'd need to plug in 1.5. And I should get 0 and -5 should take me down here. So I'm going to have this thing that scoops around. Now, what's t at when I get back to here? because I'm supposed to go between, t is supposed to be between 0 and 6. Start at 0 and go to 6. Well, by the time I get to here, t is only at 2. When I plug in 2 for t, haha, I'm going to get 3 for x again and 0 for y. It's going to bring me back to that starting spot. So clearly, to get all the way to 6 is going to take me around this loop a couple of times. And that's okay. I can repeat myself and I can go back over where I've already been. You might want to just keep in mind that sometimes it's helpful to know how many values for t did you need to plug in before you got back to the beginning. That can be helpful actually in polar more than even right now, but just in general to understand that by the time I plug in 2, I'm back to the beginning, and everything after 2 is going to repeat. So I'll be repeating what I've already done. But anyway, all they wanted to know is I do need to close this up because I'm going from t is 0 all the way to 6, so that does close that up. And then directionally, I'm going in this direction, which is not always the case that I'm going in the same direction as I go with like the unit circle. It just happens to be in this case, so you really do have to check. Now, what I haven't shown you is how to use your calculator for parametric. So this would have been a long time ago in pre-cal. So grab your calculator. Let's see if you can see it in the screen. Kind of. If we go to the graphing mode, I think, first I'm just going to zoom this standard, that I can go to menu and I can go to graph entry and put in parametric. And then I can define the x and the y separately. So this is nice. It would have taken away some of this guesswork. I would have, seen how when I got my first 2 points at 0 and 1, I wasn't sure what this was going to look like until I plugged in some fractions. So there's a lot of plugging in that happened and a lot of little mistakes that could be made. Now you can make mistakes putting your function in here too, but let's see. So we're going to have 3 cosine pi x. Oh, and we're actually going to put in t. So don't put in x, put in t, because everything's in terms of t. And then for y, we're going to have 5 sine pi t. And when you go down here, this says t is between 0 and 6.28. That means 6.28 is their approximation for 2 pi. That's the default setting. We might want to say, oh wait, we're only going from 0 to 6 instead of 6.28, so you might want to get rid of that and just go from 0 to 6. And then t step means what t values do we want them to plug in? If we just went and had them, that is literally a toilet flushing. Oh my goodness gracious, this is terrible. Hopefully I didn't just mess that up because I think I erased the equal sign. But let's see, the t step, if we just have it equaling 1, then what's going to happen is they're going to be plugging in 0 and then 1 and then 2 and then 3. They're going to be counting by whole numbers. And I should, crap, I knew that was going to happen. What did I just do? Is there an undo button on here? Crap. Okay, I have to put it all in again. Fast forward this part. Hold on one second. Okay, so sorry, the last time I kind of get rid of the equal sign somehow. So let me go back and make my t step 1. I'm nervous to back up too much. So I made it 0, 1. So that should only be giving us these points. Let's see what it looks like. Yeah, see, it didn't know how to connect for me. It made it all weird because I was only looking at certain values of t. I looked at 0, and maybe it did plug in something here. I'm not sure. But let's go back. Basically, for the t step, you always want to make it something really small. So let's go back, and even if you make it 0.1 or 0.2, the smaller you make it, the longer it's going to take for the calculator to graph it. But if you give it a nice small decimal, there we go. Now I have my like oval shape. So that's it's still just plotting certain points. It's plotting everything between t equals 0 and t equals 6 with a basically a change in t of 0.1. So it's going to plot when t is 0, when t is 0.1, 0.2, 0.3, 0.4, 0.5, all the way up to 6 and get me that shape. So as long as that t step is fairly small, it gives you the nice shape. But what it doesn't tell you is where you start and stop. So you would still need to plug in t with 0 to see where you start. Okay, those are our first two parts, part C. So keeping my graph, remember a lot of these problems do refer back to the old part. Part C, where or how many times does the particle pass through the point found in part A? So the point we found in part A was 0, 5. So it was this point here. How many times does the curve pass through that point? Well, we basically have to know how many times around am I going. So when t is 0, I start here. When t is 2, I'm back to the original point of 3, 0. So when t is 4, I'm back to here. And when t is 6, I'm back to here. So how many times did I pass through this point? 3 times. Doesn't even ask for an explanation. It'd probably only be worth 1 point. Part D, find the velocity vector. So I love when we're asked about velocity vectors because all we need to do is take a derivative. Don't forget, for anyone who forgot chain rule in the last meet, chaining on the 1/2, don't forget to chain on the derivative of the inside here. So the velocity vector means put down the fancy parentheses, and the velocity is the derivative of position. So we're going to take the derivative of the position functions. So we should get for the x, -3 times the sine of pi t times pi. Don't forget to chain on that pi. So if I want it to look a little bit nicer, I would probably say -3 pi times the sine of pi t, comma, the derivative of the y is going to be +5 cosine pi t times pi. Again, don't forget the chain, so if I write that a little nicer, 5 pi cosine pi t. That's it for velocity vector. Fancy parentheses, the velocity of the x, or the derivative of the x, the derivative of the y. All right, part E, write and evaluate an integral expression in terms of sine and cosine that gives the distance the particle travels from time equals 1.25 to time equals 1.75. So now you need to know those formulas. Yes, for us, you can look back at them. When it comes to the real test, you will not be able to look back at them. So we are going to integrate from 1.25 to 1.75. The formula is take the square root of dy dt squared plus dx dt squared. So I know I just erased it, so I would look back and I'm going to have 9 pi squared sine squared of pi t plus 25 pi squared cosine squared pi t, all the way across. And that's it. That one hopefully felt pretty easy, and hopefully you got that idea of that the curve can go through something twice or 3 times or more times, depending on what values of t they give you.